Okay, part C, same topic. Anti-differentiation, particularly useful when you're analyzing the motion of an object moving in a straight line. The position function is an antiderivative of velocity. Velocity, antiderivative of acceleration. If the acceleration and initial values, position at time zero, velocity at time zero, if those are known, then the position function can be found by anti-differentiating acceleration twice. Here's what I mean. We've done this, we did this in the beginning of the year. We talked about position function S at t. That is, your position as a function of time. Then if we took the derivative, the change in position with respect to time, we ended up with velocity at time t. So the derivative of position gives us velocity. What happens if I take the derivative of velocity? Then I get acceleration. So if I'm looking at acceleration, which is the derivative of velocity, then that tells me that the second derivative of position is acceleration. So if I start here and I want to end up here, I need to anti-differentiate once and anti-differentiate twice. So a particle moves in a straight line and has this as its acceleration function. Its initial velocity, velocity at zero, is -6 centimeters per second, and its initial displacement position, S at zero, is 9. Find the position function S at t. Okay, so let's just write this down. A at t is equal to 6t plus 4. What's velocity at t? Well, velocity at t is the antiderivative of acceleration at t. That is 6t squared over 2 plus 4t plus a constant. So my velocity at t is 3t squared plus 4t plus c. Then given this information that velocity at 0 is equal to -6, I can solve for c. So the velocity at 0 is -6. That is, -6 equals 3 times 0 squared plus 4 times 0 plus c. Therefore, -6 is equal to c. So here's my velocity function. V at t is equal to 3t squared plus 4t minus 6. Haven't gone far enough. I'm trying to find position. So in order to find position, I need to take the antiderivative of velocity. Because the derivative of position gives me velocity, the antiderivative of velocity will give me position. So S at t will equal the antiderivative of V at t, which will equal 3t cubed over 3 plus 4t squared over 2 minus 6t plus a constant, a different constant than the one we've already found. So here's my position function S at t. T cubed plus 2t squared minus 6t plus d. Solve for d. So I have my position function, given this information, S at 0 is equal to 9. Then I know that 9 is equal to 0 cubed plus 2 times 0 squared minus 6 times 0 plus d, or 9, d is equal to 9. So here's my position function. S at t is equal to t cubed plus 2t squared minus 6t plus 9. Okay, it's worth noting that this negative 6, t, was my initial velocity, and this plus 9 was my initial position. Okay, let's look at another example. We have a particle accelerated in a line such that its velocity given in meters per second, pay attention to your units, is equal to the square root of the time elapsed, also measured in seconds. How far does the particle travel in the first hour? And we have a discrepancy here in our units, so make sure that you change this 1 hour to 3,600 seconds. Okay, so we're trying to answer the question, how far does the particle travel in the first hour? Okay, so it is accelerated in a line so that its velocity, so there's going to get a little sentence here about velocity in meters per second. What does the velocity equal? The velocity at time t is equal to the square root of the time elapsed, the square root of t. And this will be measured in seconds. So if I want to know how far it travels, then it's worth noting that the velocity is always going to be positive. So if my velocity is always positive, then I know that this never moves backwards. So to find out how far it travels in the first hour, I just need to know the displacement, the distance between its starting position and its ending position. Okay, so what is S at t? Well, let's write V at t this way so that we can use power rules. The antiderivative of t to the 1/2, add 1 to the exponent, t to the power of 3 over 2, divided by the exponent, plus a constant. And fraction in the denominator means we've got 2 over 3 t to the power of 3 over 2 plus a constant. Okay, so just a little note about this constant. It doesn't give us an initial position. So we can start this kind of where we want to start it. So the sensible thing would be to start this experiment at the origin so that c is equal to 0. So let's just start at the origin. That is, if time is 0, position is going to be 0. So here's my function S at t. 2/3, and we are taking the square root of t, and then we are cubing the answer. Okay, what's t? 3,600 seconds, so 2/3 times the square root of 3,600. Find the answer to that and cube it, which is giving me 144,000, and this was going to be measured in meters. So there's my position in meters. It's not really a very logical way to answer this question. How far did it travel in the first hour? Well, let me change this into 144 kilometers in the first hour. So from a starting point at 0, to an ending point at 144. Noting that our velocity had to always be positive. We never stopped and turned around and went backwards.